Alrighty, folks. So, welcome back to another problem session. I believe this will be our next to last one. We might have two more after this. I'm not entirely certain. But we've got a number of problems from the homework this past week, and then a couple from the book. So let's get started. Alrighty. So, starting off with like number 2 on the homework. That was to or looked something along the lines of the linear approximation at x equals 0 to function that looks something like the square root of 11 minus x is a plus bx, where a equals and b equals, right? So on the computer program, there was an input box, and it wanted you to put the a and b, right? And this just because it wanted to be very clear about what was going where, right? Going back to that old problem of how does a computer understand what all the different answers should look like. Because there's a couple different forms this could come in. It might look a little bit different. So this sort of setup here is really just saying, want to make sure that you put the linear approximation into slope-intercept form, and then have those numbers be whatever they need to be to make sure you're adding here, right? So as a couple problems in this section remind you, this one doesn't say it explicitly, but the linear approximation of a function at a point is looks a lot like the tangent line, right? So we have our formula L of x equals f prime of a times x minus a plus f of a, right? So that's really just our tangent line at a solved for y. So what we need to do is figure out what's a for this problem, and then find the derivative and plug it in there, and plug it into the original function. So, in this case, the at here is the thing that gives us the clue, right? Anytime you're talking about the tangent line at a point or the linear approximation at a point, that's the a that the formula that we have is talking about. So for our problem here, a is equal to 0. And then, so all we have to do is find the derivative and we can just plug in, right? So, our function, I'm going to rewrite it slightly differently, because I prefer, personally, the chain rule to the quotient rule, and I can get away with it. So I'm going to rewrite this as 11 minus x to the negative 1/2, right? The 1/2 is because that's what the power version of a square root is, and the negative is to make sure it goes on the bottom of the fraction. So when we do that, we can use the generalized power rule, which, as a reminder, is the power rule combined with the chain rule, to bring this power down and then subtract 1 from it. Oops, I don't know why I made that so small. I needed to bring it down. Subtract 1 from it. Negative 1/2 minus 1 is negative 3/2. And then, because we're using this chain rule thing, we need to plug the inside of the parentheses back in. But then we need to multiply by the derivative of the inside. So just to make it clear here, we're going to take the derivative of the inside. So we get negative 1/2, 11 minus x to the negative 3/2 times negative 1, because that's the derivative of that linear function. So we're going to get positive 1/2 times 11 minus x to the negative 3/2. All right. So if we want f of a, we're looking at f of 0. So this is going to be 11 to the negative 1/2, or 1 over the square root of 11. If we want to look at the derivative at 0, it's going to look very similar. All right, so we're going to have that 1/2, 11 minus 0 to the negative 3/2. Right? So when I simplify this, we still have that 1 up top, 2. 11 to the 3/2 is 11 to the 1 times 11 to the 1/2. So I'm going to put the 11 to the 1 here and then just do a square root of 11. Rather than trying to do that, have 11 cubed on the inside, I'm going to simplify it by going ahead and simplifying this fraction. Right? Because this equals 1/2 times 11 to the negative 1 times 11 to the negative 1/2. Right? So this one becomes this 11, and this one becomes this square root of 11. Right? So you get 1 over 22 square roots of 11. So when we plug that into the formula here, we get L of x equals f prime of a, which we figured out was 1 over 22 times the square root of 11, times x minus 0, plus f of a, which we figured out was 1 over the square root of 11. So this becomes 1 over 22 square root of 11 times x. X minus 0 is just x, plus 1 over the square root of 11. So b was the thing being multiplied by x. So this stuff right here is equal to b. And this piece right here is equal to a. Right? Because a and b here are just the numeric constants. They shouldn't have any variables in them. Alrighty, I think that's all this one wanted. So the next question was like number 4 on the homework. So let's see, where do I have that? Right. Alright, so we have y equals sine of 3x. If delta x equals 0.6 at x equals 0, use linear approximation to estimate delta y. Right, so we have a formula from this section in the book that says delta y equals, is approximately equal to f prime of a times delta x. Now the formula might say, I don't remember if it has both versions in the book, but it might say delta f. But remember, f and y in this case are both letters that refer to the function of x. So delta y and delta f for our contexts are the same thing. Right? So if we want to figure out an estimate for delta y, we need to again know what a is. We need to know what delta x is, and we need to know what the derivative of f is. And then we can plug all that in. So again, this at is what tells us that this guy is letting us know about our a. So a equals 0. Delta x is nice and easy. They gave it to us in the problem. Right? And we have that f of x is sine of 3x. So f prime of x is going to be another one of those fairly simple applications of the chain rule, right? So sine here is the outside function, so its derivative is cosine, and then we just plug the inside in, and then we multiply by the derivative of the inside, right? So That's cosine 3x times 3, because that's the derivative of the inside. And just for convention's sake, right, there's nothing wrong with what's written here. But usually the convention is, when you simplify it, is to put your coefficients before the trig function, right? There's nothing wrong about this guy here. It's just convention to put that 3 first, right? So we need to know f prime of 0. So that's going to be 3 times cosine of 3 times 0. That's just cosine of 0, and cosine of 0 is 1. So f prime of 0 is just going to be 3. So that means delta y is approximately equal to 3 times 0.6, which is 1.8. Right, so that was the first half of the question, which was to approximate, or estimate rather, delta y using linear approximation. The next one was to find the percentage error. And this is another one where we go back to the formula. Percentage error, right, is going to be the difference between the actual true full answer and your estimation, right, divided by the actual true answer, right? So in other words, this is asking what percentage of the true answer were we away from the true answer by, right? So that's the formula that we have here. But that in itself has its own sort of smaller formula in it. The literal answer of delta y, right, what it actually is with straight equal signs, none of this wiggly business, no estimating. The definition of what that means is f of a plus delta x minus f of a, right? So this is going to be sine of 3 times 0 plus 0.6 minus sine of 3 times 0. So the first term is sine of 1.8, and the last term is sine of 0, which is just 0, right? So delta y, it turns out, is sine of 1.8. So our percentage error is sine of 1.8 minus, and we've already figured out what this was, right? That's what we did in our last part of this problem. That's just 1.8 divided by, and again we do the same delta y, so that's still sine of 1.8. We throw that into a calculator, we take the absolute value of it, and we get 0.36407, right? So that's our percentage in decimal form. If we pay attention to the user interface, if we pay attention to the program, it has a box, and then it has the percent sign after it, right? And when you put a percent sign after a percentage, then you're explicitly saying it's not in decimal form, right? Which means we need to convert this into non-decimal form, and we do that by multiplying by 100 and moving the decimal place 3 points over, or 2 points over, rather. I got confused by that 3 there that I was writing down. So 36.407% is what the program is looking for, because it's explicitly telling you with this symbol over here that it does not want the percentage in decimal form. It wants it in, percentage form. So that would be how we finish that one up. So, man, it's been, okay, good. Still going. Alright, so next one is like number 6 on the homework. So let me find that on my sheet. So find the maximum and minimum values, and I'll explain why I'm underlining that later, of g theta equals 2 theta minus 5 sine theta on 0 to pi. Right? So, when we're trying to find maximums and minimums, then there's two places that can come from. The first is the endpoints, right? So, possible maxes or mins. First off, the easy ones to find are the endpoints of our closed interval, right? If we're finding maximum and minimum on a closed interval, then the endpoints are what we're looking at here. And then the other ones are critical points, right? So whenever we do this problem, our first step is going to be to find the critical points. Then we're going to throw those in with the endpoints and check all of them and figure out which is the biggest of those and which is the smallest of those. So critical points come from the first derivative. So we look at g prime of theta, right? That means take the derivative of the first term. That just gets us a 2. Then we take derivative of the second term. The 5 is a constant multiple, so we just pull it out and leave it the way it is. And then the derivative of sine theta is cosine theta. Right? And we've got a different name now. We've usually worked with x, but the variable name doesn't matter. It's just still a variable. So there are two ways to get critical points. The first is where the function doesn't exist, and that's nowhere, right? Cosine of theta is defined everywhere for every value of theta. So there's no critical points that come from the derivative not existing. And the other category is the derivative equaling 0. Right, so that's going to be this equation. We add 5 cosine theta to both sides, and we get that cosine theta equals 2/5, which means that our solution is theta equals, or one solution is arc cosine of 2/5. Now, we have to be careful, if we recall way back to trig, right, the end of last semester, when we're solving trigonometric equations, this thing only gets us solutions in quadrant 1, right? So this is in quadrant 1, right? And if we look at our interval, this is quadrant 1 and quadrant 2, right? That's what the interval from 0 to pi is exactly equal to quadrant 1 and quadrant 2. So if we're going to get all the solutions, we need to see if there are any solutions in quadrant 2. However, if we look at this equation, right, this equation is telling me that cosine of whatever my solution is a positive number. And if we remember the way our quadrants work, in quadrant 2, cosine is negative, right? So in quadrant 2, cosine is negative, so there can be no solutions to this equation in quadrant 2, right? If this were a sine equation, right, if it said sine theta equals 2/5, then we would have to use reference angles to get another solution because sine is positive in quadrant 2. Right? But because we're dealing with cosine is negative in quadrant 2, there can be no solution for this equation in quadrant 2. So we don't have to worry about reference angles here. So Q2 gives negative cosine values. So no reference angle needed. just in case anybody's following along from the screen only, right? So that's our only critical point, right? So this guy here is our only critical point. So our possible max and mins are 0 and pi, like we mentioned before, and arc cosine of -2/5. Right, so now we have to plug all three of those in. The biggest one is the maximum, the smallest one is the minimum. Two of them are going to be easy. G of 0 is 2 times 0 minus 5 sine of 0. 2 times 0 is just 0. Sine of 0 is just 0. So that one's done. G of pi, we get 2 times pi minus 5 of sine pi. 2 times pi is just 2 times pi, but sine of pi is 0. So we get 2 pi here. Right? And lastly, we need g of arc cosine of 2/5 equals 2 cosine inverse of 2/5 minus 5 sine of cosine inverse of 2/5. Now, this one right here, right, again, if we think all the way back to trig, that is perfectly doable. We could draw a triangle, we could use SOHCAHTOA, we could fill out that triangle, we could solve that triangle, and we could figure out what sine of cosine inverse of that is. However, that would not help us figure out what the heck this number is, right? So even if we go to all that trouble, we're going to have to plug it into our calculator and get an approximation anyway. So I say, let's not waste our time when we can't get an exact value anyway. So I just plugged it in my calculator, got -2.264. So this one is our maximum, and this one is our minimum, right? Now, I promised I'd get back to why I underlined this values. And when something is asking for the maximum or minimum values, it wants the output that is maximum or minimum. So this is our maximum value, not pi, 2 pi. And this is our minimum value, not cosine inverse of 2 pi, but -2.264, right? If it wanted where we achieved our maximum value, then it would be pi and arc cosine of 2/5. But the fact that it asked for maximum or minimum values tells us that these are what we should actually put in for our answer. All right. So, next up is number 7. So, like number 7 on the homework. So that one looks something like f of x equals 3x plus 12x to the -1 has 1 local max and 1 local min at x equals input with value, there's that value again, equals input. And I guess that it showed up twice, right? I don't remember at this point, I wrote my notes, how it distinguishes between the max and the min. Hopefully that's something that's fairly easy to get when you read. All right, so this is just like we did last time. I wanted to talk about this one, though, because it has some, it is asking for local maxes and local mins, and it doesn't have endpoints, right? Last time we were looking at it on a particular interval, and here we don't have an interval, it's just in general, right? So that means that we're not guaranteed to find an absolute max or an absolute min, but we can find these local maxes or local mins. All right. So We need to do the same sort of thing. We need to find crit points. So first we take the first derivative. Right, so we take the derivative of the first term, we get 3. We take the derivative of the second term, that's going to be our power rule, so we get negative 12x to the negative 2. Right, so this is 3 minus 12 over x squared is another way of writing it. So again, we have the same two categories, but this time that does not exist one, we have a fraction that has an x on the denominator, so it does not exist when that denominator equals 0, right? And that means that x squared not equal to 0, and the only time x squared is going to be 0 is if x is 0, right? So that's one critical point. And then we need to look at f prime of x equals 0. Right, we add 12 over x squared to both sides. Right, we multiply x squared by both sides, which is something that we can do because we're already ruling out the possibility that x is equal to 0. We already know that's a crit point. We don't have to consider it, right? Because you can't multiply both sides by x squared if x could possibly be 0. The minute you do that, you're ruling out knowing anything about x equals 0. But we already know everything we need to know about x equals 0, so it's fine to do in this case. Right, so we divide both sides by 3. We take the square root of both sides, and we get that x is plus or minus 2. Right? So here's where we sort of get a look into something called the first derivative test, right? Or that's at least one way to solve it, probably the most efficient way to solve it, right? And that is I'm going to put all of my critical points on this line, and I'm going to figure out where my function is increasing and decreasing, right? Because then we can draw a brief graph of it, right? Not the actual real graph, but we can get sort of an idea of how it's going to work. So I'm going to find f prime of negative 1, right? So that's going to be 3 minus 12, so that's going to be negative. F prime of positive 1 is going to be exactly the same thing, so this is going to be even easier than it looks. Right, I'm going to fill this out. This is going to be 3 minus 12 divided by 9. Well, 12 divided by 9 is going to be smaller than 3, so I know this guy is positive. And I also know that this function is an even function, so if I put in positive 3, I'm going to get the exact same thing. Right? So, one of the things this can tell me, or if I just draw the graph is the other way to look at this one, is that we're going up in the positive ones, we're going down in the negative ones, and we're going up again in the positive ones. Right? So, from looking at this graph, or this bare bone sketch that I did here, or looking at a graph from your graphing calculator, we can tell that this is going to be a max, this is going to be a min, and this is going to be neither, right? Because critical points aren't necessarily maxes and mins. It's just that every max or min comes from a critical point. This one, of course, if we're going to throw it into a graphing calculator, right, our graphing calculator is going to make it pretty easy to find the maxes and mins without actually having to do any calculus. But if the numbers, like, instead of being negative 2 and 2 were, say, the square root of 3 and the negative square root of 3, then it's going to be really hard to find an exact value just using your calculator, right? But if you already know that those are the possibilities, your calculator can help you decide which of those they are. So this problem, doing the calculus is a little bit extraneous, if we're just going to pull out a graphing calculator anyway. But we can also do this and just check a few values here, right? So we'd have x equals -2 with value, let's see, what do we get? Yeah, let me do some work before I start to write out a final answer. So we do want the values, right? Remember, value means what we get when we plug in. So f of -2, not f prime of -2, but f of -2 is 3 times -2 plus 12 divided by -2. So this is -6 minus 6, or -12. F of +2. One thing we can note is that f is an odd function. So we know it's going to be +12 from that, but we can also just plug in and get 12 that way as well. Right? So we're going to have x is equal to -2 with value -12, and x is equal to +2 with value +12. Right? Would be what we want to input into the homework program. All right. So next up, we have so next one we actually have working the same sort of way as 7 did, or the next one that was asked about. Let me back up and be clear, because I'm not going to actually go through all the work here. But number 8 was also asked about, but it works a lot like this one, right? The difference being that it explicitly asks where it's increasing and decreasing, right? And you get that from this chart we made right here, right? So that's another reason why I did it on this problem, though we didn't necessarily need it. Is because it sort of works for problem 8 too, right? We put in our crit points, and the other one has end points, so we do need to throw the end points on there. But then we figure out where the derivative is positive, and that's going to be increasing, where it's negative, and that's going to be decreasing. And we find the min and the max by doing this drawing or plugging it into a calculator. And then the question where f of x is positive, that's a pre-calculus question. Yeah, so it works just like what we did sort of in this portion, with the added wrinkle that we do need to consider the endpoints, right? But that just means drawing them on here, and having them work as a thing, right? So, and we could also, at that point, since we are working on an interval, we need to do this to answer the increasing and decreasing portion. But for the max and min portion, we can actually do the same thing we did here, right? Solve for the derivative being 0, or solve for the critical points. Take all of the critical points that you might find, as well as the endpoints, and plug them in and see which of them gets you the biggest and which of them gets you the smallest. One sort of thing that I will do for this one, is an algebra trick that might get lost as we do it. And I know that was specifically part of the problem, was finding the max and min. So just in case it was an algebra issue there, right? We have a function that looks like right? And so when we find the critical points, we want to take the derivative. This requires the product rule. So we take the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece. And then, so the trick here is that while this would be really obnoxious to multiply out and then factor again, is that there's actually some very common factors in here, right? And what's going to be left over, because of the way we got this, is always going to be linear pieces, right? So it's not just the numbers that I chose make it nice, but since this comes from the product formula, what's left over is always going to be linear. So we can't take out that 5 because there's not a 5 over here, but we can take out 4 x's, right? We've got 4 x's here, we've got 5 x's here, we can only take out the minimum. So we can take out x to the 4th. Then we can take out 3x plus 2. We have 6 of them here and 5 of them here, so we can only take out 5 of them. Right, so that leaves over here 5. We pulled out all of the x to the 4th, but we have one of these left. 3x plus 2. And we took out all of these this time, but we still have a 6 and one of these x's left. So we get x to the 4th, 3x plus 2 to the 5th. So this makes 15x plus another 6 is 21x, and plus 10. Right? So considering that what we want to do to find critical points is set this equal to 0, having it be in factored form is ideal. Right? So rather than multiplying all that out and trying to refactor it again, which would just be horrible, we can just pull out some common factors, and maybe that'll make it a little bit easier to work on that maximum and minimum problem, right? Because otherwise it works exactly like 6 to find the max and min, and it works exactly like what we did in 7 to find the increasing and decreasing. So we'll leave that with that. So, and the next one was like number 10 on homework. So we have a function f of x equals 1 over x on 2 to 7. So it asks to find the average or mean slope, and then find a c that satisfies the mean value theorem. And I didn't write down the wording exactly, which I probably should have, because that might be one thing that trips some people up. I know it does. I did say average or mean slope and right, and that wasn't saying that you get to choose one of those and find. It's saying that that's two different names for the same thing, right? The average slope and the mean slope are the same thing, and what that is remember, slope is the rate of change, right? So this is just the average rate of change, right? It's the change of y over the change of x, right? And if we remember the mean value theorem, that says that there's some value c so that f prime of c is equal to that average slope, right? I'm not sure our book called it an average slope, but it did call it something like an average rate of change, and the formula is certainly the same as the slope. So what it's saying is find this number and then find a c so that this whole statement is true, right? So first we'll find that number. That's pretty easy, right? So b is always the second endpoint, a is always the first endpoint. So the average slope is 1 over 7 minus 1 over 2 all over 7 minus 2. So I want to get a common denominator of stuff up top. So that's going to be 2/14 minus 7/14 all over 5. So negative 5/14 over 5. So negative 1/14. Right? And if I want to find an f of c that's equal to that, or a c so that f prime of c is equal to that, well, I need to know f prime of c. So, or f prime of x, rather. And then f prime of c. So f prime of x, so just as a note up here, f of x equals 1 over, x to the negative 1, right, is another way to write that. So f prime of x is going to be negative x to the negative 2, or negative 1 over x squared. Right, so we want this statement to be true, so we want negative 1/14 to be equal to negative 1 over c squared. Right, and it's pretty clear from the way this is laid out that that means that we want 14 to be equal to c squared. So c is equal to plus or minus the square root of 14. Right, now this problem says find AC, right, and we need to keep in mind that this formula is not just going to be true for some number period, it's going to be for some number in this interval. Right, so negative square root of 14 is not in between 2 and 7. Positive square root of 14 is. Right, so our final answer is going to be c is equal to the square root of 14, because that's the only one of our two possibilities that is in the interval that we care about. Right, so that's all that question was asking for. I realize that there was probably some wording issues there, but that's sort of what it was looking for. Okay, so we're at the end of this file, so time to start up a new one. Alrighty, we have one more problem from the homework. And it's a lot like 8 and 7. Again, worded a little bit differently, and there's something that I want to talk about here. Of ways that we can sort of get through things here. So first it said, well, f of x is equal to 13 minus 7x to the 8th. Right, and it said find the critical value. And I believe it implied that there's only one. And it asked, what does f do to the left and right of that critical value? Right, and it gave you a drop-down menu, and you can choose increasing or decreasing. Right, so what does it do is a little bit vague as I have it here, but there was a drop-down that sort of gave you an indication here. Right, so critical values means taking the derivative. So this is going to be a generalized power rule. So we take that power, we leave the inside the way it is, and we drop the power by 1, but then we multiply by the derivative of the inside, and the derivative of the inside in this case is just negative 7. So we combine all that together. And this is a polynomial. Polynomials exist everywhere. So the does not exist does not apply. F prime of x equaling 0. Well, thankfully, this guy stays in factored form because we don't have a product rule going on. So this is going to be when its one factor is equal to 0. So we get 13 equals 7x. So x equals 13 divided by 7. So again, we're sort of looking at this guy. And I partially wanted to do this because, there's a nice trick that I want to remind y'all. You might have forgotten, you probably hadn't used it in a while. But I'm gonna pick a number over here, because that's gonna be really easy to plug in. Right, if I plug 0 in, I'm raising 13 to the 7th. I don't know what number that is, but it's positive. And negative 56 is, well, it's negative. So I know that this whole side, right, because polynomials can only change sign at zeros, and polynomials was not necessarily their functions. Continuous functions can only change positive or negative at 0. So this whole thing is going to be negative. And we notice that this 0 has multiplicity 7, right? So if you can dredge way back in your mind, back to pre-calculus and remember how multiplicities work. Multiplicity, if it's odd, then this is going to change. If it's even, it stays the same. So this multiplicity is odd. So as we cross over that 0, this guy changes to positive, right? If that had been a 6th power up there, then it would have stayed negative on both sides, right? But the fact that it's an odd power means that it started out negative and went positive. Now, of course, if you don't remember that, you could always just do something like, I don't know, plug in 2, and figure out that you got a positive number out of that, right? There's nothing wrong with that. But especially in this case where you're just checking like one more thing, right? For a problem, say like number 8 or number 7, we could have simplified it by just finding one of those values and then using the multiplicities of the zeros to hop to the rest of them. Right, and so we know it's decreasing to the left and increasing to the right, because a negative derivative means it's decreasing. A positive derivative means it's increasing. Yeah. Right. Okay, so that was all the questions folks had about the homeworks. So about the problems from the book, we had a couple of those. So from section 4.4, number 13, it said y equals 1 over x squared plus 3. So this one, the instructions were to find the points of inflection, and the intervals where the function is concave up and down. Right, now this works a lot like the stuff that we just got done talking about for the homework, except it's all for the second derivative, right? Concave up and concave down are the equivalents to increasing and decreasing, but if we're talking about the second derivative instead of the first derivative. And points of inflection are a little bit like critical points. At the very least, we find something like critical points for the second derivative first, and then we figure out which of those are actually inflection points. So, all of that to say that we need to find the second derivative, right? So I'm going to go ahead and rewrite this as x squared plus 3 to the negative 1, because as I mentioned, I prefer the chain rule to the quotient rule when I can get away with it. So we get x squared plus 3 to the negative 2, and then we take the derivative of the inside, right? So x squared plus 3 derivative, so this is negative 1 times x squared plus 3 to the negative 2 times 2x. And here's where my preferences break down, because once we have something that looks like this, right, specifically this, where we have to use the product rule and then the chain rule and all of that, it really starts not getting any worse than using the quotient rule. In fact, when I first started writing up this problem, I did it using my usual way, like doing this and doing the product rule and the chain rule, and all of that stuff, and I wound up making some sort of algebra error that made the whole problem a heck of a lot harder than it needed to be. So I went back through and did it again because something wasn't feeling right there. And I did it using the quotient rule, and everything turned out hunky-dory, and it was super simple and a lot easier than I made it. So, I do recommend using the chain rule in this situation instead of the quotient rule, I would be cautious about using it if there's anything complicated up top. Right? And that doesn't necessarily mean you need to not do it. It just means you have to be really careful about it. Right? So for y double prime, I'm going to use the quotient rule. Right? So low is going to be x squared plus 3 squared. So d low is going to be 2 x squared plus 3. You know what? There's no need for me to try to shoehorn this in. Let's do low equals x squared plus 3 squared. D low. We're going to do the generalized power rule for this one, certainly. Right, so we've got we bring the power down, we drop the power by 1, we leave the inside unchanged, but then we multiply it by the derivative of the inside. And we get this. Then high is negative 2x, and d high is negative 2. So y prime is going to be low d high minus high d low over the square of low we go. So, it's not to say that everything's going to be easy. You know what? I'm going to go ahead and pull that negative 2 out. Probably should have done that from the very beginning. But I get bottom's not going to change for a bit. Pull that negative 2 out, so this just becomes this piece. This negative 2 is going to be the thing that I pull out, so I get 4x squared. Now, this is kind of like what we did in problem, what was it? I've forgotten already. Problem. Why can I not find it? I swear I flipped the same piece of paper over like 3 times looking for it. Problem 8. When we did out that algebra, I wanted to show that trick, right? Because we can pull out an x squared plus 3 from both terms up top, right? So we get a negative 2 times x squared plus 3. Then we have left over in this term, we still have an x squared plus 3 left over. And in this term, we just have a 4x squared left over. And that's even nicer in this case than it was in problem 8, because this x squared plus 3 and this cancel out. And we're left with x squared plus 3 minus 4x squared all over x squared plus 3 cubed. All right, so we do a little bit more algebra, and we get negative 3x squared plus 3 all over x squared plus 3 squared. I'm going to pull a negative 3 out of that, so we get 6 times x squared minus 1 all over x squared plus 3 cubed, rather, not squared. Now, that's a heck of a lot better that I got than the first time I tried this. Right, but what we want to do to this, right, we want to find those points of inflection and where the function is concave up and concave down. So we need to find those things that are similar to critical points. So we want to find where this does not exist. Right, so in this case, that would usually be where the denominator is equal to 0, right? We have a fraction, so there's the potential that this doesn't exist, but that's never. Right, x squared is always positive, 3 is always positive, so this number is always going to be bigger than 0. So, I mean, we could solve it a little bit, and we get that x squared is equal to negative 3, and we know that that doesn't have any solutions. Right, so the other option would be that y double prime is equal to 0. And we can cheat a little bit, right? This is something you can always do when you're looking at rational functions. Rational functions only ever equal 0 when their numerator equals 0. So I can even get rid of that constant in the numerator and say that y double prime is only going to be equal to 0 when x squared minus 1 is equal to 0. Right, so this is x squared equals 1. So x equals plus or minus 1. Right? So we have our potential inflection points. Right? So here's where we want to draw our number line again. We want to put our potential inflection points here. And then we want to build on it. So we want to do that plus and minus thing. So if we take our second derivative and we plug 0 in, up top we get a negative number. Down below we get a positive number. So a negative divided by a positive is negative. Then we notice that, right, because really this multiplied to x minus 1, x plus 1, right, and that's where we got to these, or that's the way we would get to those using factoring, right, and that's how multiplicity comes into things. So we can see that each of these has a secret multiplicity of 1, right? Usually we don't draw that power, but it's still secretly there. So that means that both of these should change. Right? So again, that's using multiplicities. You could also do something like plugging in 2 here. And then we get 4 minus 1. That means the top is going to be positive and the bottom's always going to be positive. So a positive divided by a positive is still positive. Same for over here. We could have done y double prime of, I don't know, negative 3. And we've got 9 minus 1 is positive, times a positive, divided by a positive, so this guy is also positive. Right, so the rules for inflection points say that these things that are like critical points, right, that we got using these two rules, are inflection points if the sign changes. Right, so the fact that this went from plus to minus, and then minus to plus, say that negative 1 and 1 are both inflection points. Right? That positive and that negative also tell us about concave up. So it's concave up when the second derivative is positive. So from negative infinity to 1, and from 1 to infinity, it's concave up. And from -1 to +1, it's concave down. Right, so same ideas for increasing and decreasing, just using the second derivative instead tells us about concave up and concave down. Right, and these guys, I really wish there was a name for the the step before we get to inflection point, but the thing that behaves a lot like critical points, but for the second derivative, are always going to be inflection points if it changes either from positive to negative or from negative to positive when it crosses over that 0. Right. Alrighty. And our next one was from section 4.5, and it was number 49. So this was to find the limit as x goes to 0 of cosine of x to 3 over x squared. Right, so if we were to do substitution, right, first, cosine of 0 is just 1, so that's looking promising. But this is going to 3 divided by 0, which is, we've talked about before, anything, when we're taking the limit, if we're dividing by 0, that's the same thing as the concept of infinity. Right, so this is that indeterminate form that looks like 1 to the infinity. Right, it's one of the indeterminate forms talked about in this section, and it's one of the ones that we deal with by looking at the logarithm instead. So we go ahead and set y equal to this guy, and then ln of y is equal to ln of cosine x to that. And we can use the power rule for logarithms to say that this is 3 over x squared times the natural log of cosine x. Right. And we're going to hope that this gets us around it. I'm going to rewrite it a little bit different because it'll be handy. And hopefully this will give us something that we can find the limit of, right? So we're going to look at the limit as x goes to 0 of ln of y. So this is the limit as x goes to 0 of 3 ln cosine x over x squared. And if we do substitution, right, bottom's easy, that's 0. Right, so cosine of x, as we've mentioned, when x is 0 is 1. Ln of 1 is also 0, so we have a 0 over 0, right? So it's another indeterminate form, but it's the much nicer version of indeterminate form that actually plays well with L'Hopital's, right? So that means that this guy is going to be the same limit as what we get if we take the derivative of top and bottom. Again, the derivative of the bottom is pretty simple. It's 2 times x. Up top, the 3 is a constant, so we can pull it out. And then we know from previous sections that the derivative of the logarithm of something is the derivative of that something, so negative sine x, divided by that something. Right, so this is using the rule, the derivative of ln of f of x is equal to the derivative of f of x divided by f of x. Right, so here the f of x is cosine of x. So we get this guy. That looks a little bit obnoxious, so I'm going to simplify this. Now, unfortunately, when we do substitution, we get 0 over 0 again. Right? 2x, obviously 0 when x is 0, and tangent is also 0 when x is 0. So, we got 0 over 0 again, nothing to do but L'Hopital's. Right? So, this is going to be the same thing as taking that same limit, but taking the derivative of top and bottom. So, I turn back a few sections and look up the derivative of tangent. and see that that's secant squared x. The derivative of 2x is just 2. So this one, when I do substitution, I get negative 3 times 1 over 2. So that is a nice, defined, happy, solid number. But we're not quite done yet, right? Because this was the limit of ln of y, and we wanted to know the limit of y, right? So this guy is the limit of y. But it turns out that that's not too bad. Let me get it all written up here. Right, this is the limit of y as x goes to 0. It turns out that limits play nicely with powers, so this is the same thing as e to the limit of ln of y. And we already figured out what that is. That's negative 3/2. So the limit of the thing we were looking at originally is e to the negative 3/2. Right? So it turns out that throwing something through a logarithm is actually really nice, because it can turn these sort of exponential indeterminate forms, right? Because 0 over 0 is also a thing that can cause problems here. So it can turn these exponential indeterminate forms into a 0 over 0 one, and then we can use this rule to get back to where we wanted to be in the first place. Right? So, that was the last question I got on the sign-up page this week. I hope everybody enjoys their Thanksgiving break. And I'll see you on the other side. Keep in mind, do pay attention to the due dates. They're on the schedule spreadsheet as well, where it's not going to be quite as simple as Monday to Friday as things have been, because of the way the holiday is falling into things. So do pay attention to when those assignments are coming out. And I'll see y'all on the other side.